Thank you.
Thank you very much, Mike. On behalf of Georgia Tech, let me welcome to this 60th Colloid and Surface Science Symposium. Over 500, I'm told, speakers, industrial representatives, and guests from 35 states and 15 foreign countries who will be speaking, according to your program, on such topics as absorption, catalysis, cellulose, flocculation, enhanced oil recovery, molecular sieves, emulsions, fine particles, and lubrication. It is very appropriate that Georgia Tech has been chosen as the site for this symposium, since surface science involves so many areas represented here at Georgia Tech. We particularly recognize the importance of multidisciplinary activities. Among our formal multidisciplinary programs are mining and mineral resources, materials engineering, polymers and plastics, pulp and paper, energy engineering, and textiles. We're also particularly pleased to be your host this time because this is Georgia Tech's centennial year, which is old for this country, not so old compared to places where some of you come from. But from this original campus of 9 acres, Tech now occupies 320 acres and 128 major buildings. Our total enrollment is about 11,000 students, consisting of 20% graduate students, 20% women, and 10% minorities. We organized into 4 colleges: College of Engineering, which is by far the largest with 75% of our students, College of Sciences and Liberal Studies, Management, and Architecture. Georgia Tech is working to become one of the nation's top-ranked research universities, conducting both theoretical and applied research through these academic colleges and the Georgia Tech Research Institute. Current level of our research expenditures is about $85 million per year. An interesting fact is that Georgia Tech is among the largest industrially funded R&D universities in the country, with over 20% of that support coming from this source. Well, we're all proud to mark the first of our 200 years with such a distinguished conference as this. I hope you enjoy your visit. If in this busy schedule that you have mapped out for you, it would be great if you could have a chance to see some more of Georgia Tech. But anyhow, enjoy your visit, and I hope you'll find this meeting stimulating both intellectually and socially. Thank you very much.
Main speaker for this morning.
Well, it was just 15 years ago that I guess the 45th National Colloid, and I don't know if it was called the Surface Science Symposium at that time. We were trying to get the name changed, but it may have just been the National Colloid Symposium. And I had the pleasure of introducing the 2 plenary lecturers for that time, André Bellemans from the Netherlands and George Halsey from the University of Washington. So I was real pleased when Mike asked me to introduce the plenary lecturer for this morning. I first met Professor Singh must be about 12 years ago, attending a conference at Clarkson. Rode in a taxi with him from the airport, and of course I realized who he was, the Greg and Singh, so I was really quite honored to share the cab with him. So it's very nice that I can introduce him today. Professor Singh obtained his Bachelor of Science degree from London University in 1945 with first-class honors in chemistry. He went on to obtain his PhD, also at London and Exeter, and obtained his, I guess it was Exeter at London, and then obtained his Doctor of Science degree from Exeter in 1970. His first effort was to go into industry. ICI had him come out and visit, and they immediately made him an offer after his PhD work. And so in 1948 he went as a research scientist with ICI, remained there a year. The yearnings for academic work were very great, and so he went to Salford Technological College, where he was a lecturer in physical chemistry and then a senior lecturer, and remained there until 1956. 1956, he became the head of the chemistry department at the Liverpool Polytechnic Institute, and then in 1965 was the first professor of chemistry at Brunel University and head of the Department of Chemistry at Brunel. It was the beginnings of Brunel, which has now grown to a very attractive and impressive university in London. He is now, as of 1984, a senior research professor at Brunel. He is currently, or is just past, chairman of the IUPAC Commission on Colloid and Surface Chemistry, and he's a member of the British National Committee for Chemistry. He has over 100 publications in gas-solid systems, adsorption of gases on solids, many review articles, and of course his famous book on surface areas and porosity, published with Professor Gregg, which is now in its second edition and is published in a number of languages. His travels include trips to Russia, Lebanon, Egypt, most, if not all, of the European countries, Australia, Canada, and of course the US. In fact, in this particular year, I think it was in December, he spent several weeks in Australia. In April, he was in the United States as one of the organizers and feature lecturers at the conference on carbon at Hilton Head. He then came back to the United States in May, where he was organizer and lecturer at a conference on fundamentals of adsorption at Santa Barbara. And he has returned now. I guess he saw what lovely weather they've had in Hilton Head, and it was lovely, and then Santa Barbara, and now he came back to get a little bit more warmth. He's a consultant for many companies. In fact, on this particular trip, he has visited Cyanamid, Dow, Exxon, and I don't know whether he visited West Vaco on this trip or in the past trip. It's a real honor and pleasure for me to introduce Professor K.S.W. Singh from Brunel University, who will speak on the significance of the contributions of A.V. Kiselev.
Well, thank you very much, Professor Pirotti, for that over-generous introduction. Mr. Chairman, Mr. Vice President, ladies and gentlemen, the news of the death of Andrei Vladimirovich Kiselev on the 17th of July 1984 came as a great shock to his many friends in the world community of surface scientists. Many, I'm sure, will share my view that Kiselev should be regarded as one of the leading Soviet scientists of his generation, and indeed, I think, one of the leading scientists of our time. He was born in Moscow in 1908. Could I see the... let's go back to that one. There we are. There's a rather formal picture of Kiselev to start with. He was born in Moscow in 1908. My impression is that his family background in pre-revolutionary Russia was fairly well-to-do. In fact, we see him here in a less formal situation in his apartment, which was situated in one of the wings of the M.V. Lomonosov State University of Moscow. As you can see, the apartment itself was a kind of stately home in miniature. It was crammed with family heirlooms and antiques of various kinds, old clocks and furniture, including even an English 18th century grandfather clock, French porcelain, and many old prints and documents. Kiselev was interested in all the visual arts, not perhaps so much in music, but was passionately fond of ecclesiastical architecture And as I'm sure a number of you will know, as Professor Bauer will remember, it was always a joy to accompany Kiselev on any excursion to a cathedral or ancient church or abbey. I first met him, you might say I first came under his spell in 1957 when he made his first visit to Britain. He came to Britain on 3 occasions, as far as I recall, during the 1960s. I was privileged to visit him in Moscow in 1965 and again in 1968, when I spent a few months in the Soviet Union, mainly with him in his laboratory. The last time I saw him, I think, was in 1974, and by that time it was becoming difficult for him to travel to the West. He was always delightful company as both guest and host. He had a strong sense of humor, which was manifested in his personal motto, always in trouble, but always hoping for the best, which he would declare with a twinkle in his eye whenever he felt it was appropriate, which in fact was fairly often. Kiselev stood outside, or perhaps I should say above, politics. I'm sure that he was a good Soviet citizen in every respect, but time that I spent with him, I never heard him speak ill of the United States or of Great Britain. This feeling of always in trouble was perhaps the driving force which resulted in the colossal output of over 900 research papers and reviews. Surely this is a record which is worthy of inclusion in the Guinness Book of Records. Obviously, the enormous output of papers, research material, poses a tough problem for any reviewer of Kiselev's work. In the space of my remaining 50 minutes or so, it's clearly out of the question to attempt to provide an overall assessment of his achievements. All I can hope to do is to highlight particular aspects of his work, which, of course, I believe to be of current interest and of lasting importance, and which, to some extent, must reflect my own interests. And I shall try also to make a few suggestions concerning the future and the assessment of our needs in this important area of research. At the risk of oversimplification, I think that we can subdivide Kiselev's major research activities into these 4 main areas. First, we see his work on the energetics of physical adsorption, that is, the experimental determination of heats of adsorption and the theoretical calculation of gas-solid interaction energies, which were carried out, as we shall see, for a wide range of different systems. Secondly, his studies of adsorption equilibria, particularly the determination of adsorption data under standardized conditions and for carefully well-defined systems, and his molecular statistical treatment of gas-solid adsorption equilibria. Thirdly, we see the development and the exploitation of gas-solid and liquid-solid chromatographic techniques for the determination of adsorption data and the design of new chromatographic procedures for the separation of many different types of molecular and macromolecular systems, including complex molecules, organic isomers, proteins, polymers, etc. And then finally, the application of a range of surface chemical methods, notably calorimetric, chromatographic, and spectroscopic techniques for the characterization of solid surfaces. Next, we see the range of solids, the adsorbents, which were studied at various times by Kiselev and his co-workers. I don't pretend that this is a comprehensive range, but I think that it is, in fact, fairly complete. In his early work, that is before the Second World War, he was concerned mainly with porous carbons and silica gels. But I think that he was one of the first to appreciate the opportunity offered by the development of the materials, well-defined systems, especially graphitized carbon blacks and the aerosol grades of silica, to study well-defined and reproducible non-porous solids. And this work was certainly started very soon after the war and came to our attention, in fact, in 1957. In the early and mid-1960s, the attention of many Soviet surface scientists, including Kiselev, Dubinin, Zhdanov, Zvishishvili, and many others, was turned towards the molecular sieve zeolites. And these materials have remained a major interest to Soviet scientists, surface scientists in the Soviet Union for the past 20 years. The other adsorbents on the list have been investigated, I think, for the most part, in the context of gas and liquid chromatography. Well, next, let us look in some detail at the work of Kiselev on the energetics of adsorption. It's hard to believe now that these measurements of the differential heats of adsorption of normal alkanes on graphitized carbon black were reported as long ago as 1957. They were obviously carried out over 30 years ago and reported at the Second International Congress of Surface Activity in 1957, which was held in London, England, in 1957. Here we may note that the small residual energetic heterogeneity of the graphitized carbon black, and also the effect of the adsorbate interactions coming into play in the region where the monolayer is beginning to build up in concentration. So we see this increase in the heat of adsorption, the energetic heterogeneity in the first place, and then the increase in the differential heat of adsorption, increasing during the course of the monolayer buildup, and then, of course, the rapid fall-off with the completion of the monolayer. And I think this is probably the first time in which these effects were so clearly documented. Also, in the same period, Kiselev and Isarikian, detailed paper being published in 1961, this work appeared, but was also referred to in note form in the 1957 conference, Surface Activity Congress. We see here again, I think, perhaps for the first time, the clear difference between the adsorbate interaction, which is coming into play in the case of normal hexane, and which is virtually absent for benzene. And of course, the explanation of this difference is in the configuration of the adsorbate molecules, the benzene molecules lying relatively flat on the basal plane, graphitized surface, and undergoing comparatively little interaction with each other in comparison with the pronounced interaction that we see here and we saw just now in the case of the normal alkanes. And that came out very clearly in that early work and has been, of course, confirmed since that time by many other workers. It was about 25 years ago that Avgul, Kiselev, and Poshkus began to make their elaborate calculations of adsorption energies for a very wide range of simple and complex molecules adsorbed on the basal plane of graphite. In fact, the underlying principles of their approach were not new. Their calculations were based essentially on the procedure first proposed by Professor Barra in 1937. Their work of Kiselev and his co-workers involved the summation of the pairwise Leonard-Jones potential as had been done by others, but with the inclusion of a number of refinements in the calculation of the dispersion and polarization terms. In this manner, as you see here, Kiselev was able to obtain remarkably good agreement between the corresponding theoretical and experimental values of the adsorption energy. So we see the plot. I don't know whether, could we lower this, please? Can we bring it down a little bit? Projectionist? If we can lower it, please. Lower the slide down. Well, maybe not. It doesn't matter too much. Okay. We see enough of it anyway to see the plot here of the calculated values of the, can't see the axis labeled, but this is calculated values of the interaction energies in comparison with the experimental values measured by calorimetry, adsorption calorimetry. And you see here, with certain semi-empirical adjustments, you see a remarkably good correspondence over this very wide range of adsorbate polarizability. Now, in the mid-1960s also, the concept of specificity of physisorption was developed thanks largely to the work of Professor Barrer in Britain and Professor Kiselev in the Soviet Union. And in this context, Kiselev put forward a classification, fairly detailed classification of adsorbents, as we see here, and adsorbates. You see the reference to the review paper by Kiselev, which certainly is a very important paper, I think, to refer back to. A paper in the Discussions of Faraday Society, as it was then, in 1965. So this we see as a classification of adsorbents, excuse me, of adsorbents. In class 1, we see the least complicated adsorbent systems, notably graphitized carbon black, to which I've referred already. In these cases, the interactions are primarily involve the dispersion forces and the short-range repulsion forces. Class 2 and 3 adsorbents always involve some form of specificity when interacting with polar molecules. We shall look at this in a little more detail in a moment. In 1966, in a review paper, which is referred to here, General Colloid and Interface Science paper, Barrer proposed a simple but very useful expression for the overall adsorption energy, as you see. This is a good approximation and can be used to subdivide the various contributions to the interaction energy which can come into play for particular systems. The first 3 terms, of course, refer to the non-specific contributions, the dispersion, repulsion, polarization contributions, which, as I've mentioned, always play some part in the adsorption process. Although the polarization term itself is often neglected in the case of the adsorption of a nonpolar molecule on a class 1 adsorbent. The field dipole and the field gradient quadrupole terms, field dipole and field gradient quadrupole terms, must be taken into account when polar molecules are adsorbed on class 2 or class 3 adsorbents. And the final term, the self-potential term, of course accounts for the adsorbate interactions, which, as we've seen, normally become important as the surface coverage is increased. And those, of course, can be neglected at very low surface coverage. At effectively zero coverage, those are no longer need to be taken into account. In the 1960s also, Kiselev and his co-workers studied in great detail the changes in the adsorptive properties which are produced by the removal of hydroxyl groups from the surface of non-porous silica, the aerosol grades of non-porous silica. They demonstrated that the heats of adsorption, differential heats of adsorption of polar molecules, and we see here some relatively simple polar molecules, nitrogen with its permanent quadrupole moment, benzene, pi-bonded system, and ether, ethyl ether, all polar molecules. The heats here, as we see, were drastically changed as a result of the surface dehydroxylation. So we see the decrease in the position, each one of these curves, accompanying the removal of the surface hydroxyl groups, which was taken to signify then the reduction, almost complete removal, in fact, of the specific contributions. This effect appeared to be in complete contrast to the virtually undetectable change, as you see here, which was reported at that time with non-polar molecules. Here we see the curves reported in the 1960s. A number of papers published in the 1960s showed essentially these same results for argon, carbon tetrachloride, and normal ethane. And there were other non-polar molecules which were studied in a similar manner. And by the end of the decade, the overall pattern, therefore, seemed clear, and it only appeared necessary to fill in the details for more complex molecules. In fact, as it turned out, any tendency towards complacency was short-lived. And in the early 1970s, several new aspects came to light, which seemed at the time to cast considerable doubt on the earlier interpretation. First, it became evident in 1971, in another paper contributed by Kiselev to a Faraday discussion, in a Faraday discussion on oxides, which actually was held in my own university, Brunel University, in 1971. Paper which appeared in the proceedings, but which unfortunately was not presented in person by Kiselev, gave a detailed account of the complications which had been detected in connection with various grades of silica aerosol, which were previously thought to be pure and which were found to contain significant amounts of aluminium. And it was shown quite clearly in this work that the presence of the aluminium could produce a marked change in the adsorptive properties of the dehydrated material, that is, after the heat treatment at temperatures of around 1,000 degrees centigrade. By the application of various spectroscopic techniques and the study of the adsorption of organic bases, it was demonstrated that strong acid sites were formed in the course of the dehydration through the presence of the surface aluminium, a result that perhaps we shouldn't really find so surprising now. To avoid this complication, the Russian workers carried out another series of careful adsorption measurements using pure silica, which had been specially annealed in a hydrothermal treatment, and this material they referred to, and in fact have published a good deal of work in recent years. The material has been named aerosilo-gel. An important paper was published in 1974 under the names of Kurtois, Davidov, A.V. Kiselev, S.A. Kiselev, and Kuznetsov, which summarized, I think I give the reference here if you can read it, probably can't, it's right down the bottom, Journal of Colloid Interface Science, Al Settlemore will be pleased to know, 1974. This was, in my view, an extremely important paper, but I recall that my own first impression when I saw these results was one of surprise and bewilderment. Because what we now see is that all the heat curves, the differential heat curves, are displaced downwards, including those, as you see, for the non-polar molecules. So we see here normal hexane, cyclohexane, carbon tetrachloride. All these curves now move downwards to a significant amount. Not a small movement, it's really a very drastic change in the location of all those curves as a result of a surface dehydroxylation, or apparently as a result of surface dehydroxylation. And this then is the result of outgassing the pure silica aerosilo-gel at temperatures of around 1100 degrees centigrade. The explanation given for these results was that is the results with the non-polar adsorbate molecules, was that the phi-p contribution, the polarization contribution, was likely to have been reduced as a result of the low residual surface OH group concentration, which followed the high temperature treatment. I've read the paper very carefully, and that is virtually the only comment that I see. Now, I feel myself that the scale of this change suggests something more, that probably the dehydroxylation process was accompanied by the removal of surface irregularities. So there was a further smoothing of the surface which took place as a result of this high temperature outgassing treatment. And I think, therefore, if this is true, if that hypothesis is true, it would be of interest to explore the effect of rehydroxylation to ascertain whether the original curves would be restored or whether the upward movement would then not take place at all or take place to only a limited extent. So that's one point of interest about this work. I believe that these results are of considerable significance because they reveal that it is possible to prepare a silica surface having a very high degree of energetic uniformity. Indeed, we can even observe the unambiguous evidence of adsorbate-adsorbate interactions of the kind that I've mentioned already. As you see here, in the case of the normal hexane, there is a slight but quite significant increase in the heat of adsorption, and it's taking place here. The net differential heat is, of course, negative in the first place in this case, as it is here, and in each case moving upwards as a result of cooperative interactions between adsorbate molecules. In the case of benzene, the heat remains almost constant, as you see, over a very wide range of surface coverage. And those are remarkable results, it seems to me, when we appreciate that they're obtained with an oxide surface, not with graphitized carbon, but with an oxide surface. This paper, as far as I've been able to see from the literature, the subsequent literature, has not received the attention that it deserves. And I think we can learn a great deal when we look carefully at that work. Now, in view of the low heats of adsorption recorded here and the negative heats in some cases, it's not surprising to see that a number of these isotherms are in fact of type 3, truly type 3. This is, of course, a notable result. So I think that these results, taken together, reinforce the views that some of us have expressed in recent years, that it is very important to obtain standard adsorption data on well-defined surfaces. In a 1973 paper published again in the journal Colloid and Interface Science, Avgul, Bezos, Dobrova, and Kiselev pointed out that equations of the virial form, you can just see part of this at the very bottom, here we are. This is a particular form of the virial expansion, which has been, of course, used by a number of other adsorption scientists in other types of expressions, mathematical expressions. So there's nothing new about this, but these workers pointed out that this form of equation can be applied to adsorption data not only obtained over a wide range of temperature, but also obtained with both non-porous and microporous solids. Obviously, the individual values of the coefficients and the Q heat terms must depend on the nature of the particular gas-solid system. Kiselev had introduced other forms of adsorption isotherm equations in his earlier work, but in the later work, dating from the 1970s, he preferred to use this type of expansion, which, as you see, is a very versatile one and will fit data of this kind remarkably well from the low coverage right up into the middle coverage region. In their 1973 paper and in other publications, in fact, Kiselev and his co-workers metaphorically crossed swords with their distinguished compatriot, academician Dubinin. They drew attention to the limitations of Dubinin's approach and to the theory of micropore filling, and in particular to the empirical nature of the Dubinin-Radushkovich and the Dubinin-Astakov equation. It was further argued that in favorable cases, the virial expansion provides a convenient way of separating the adsorbent, adsorbate, and adsorbate, adsorbate terms, and therefore of analyzing the region, the isotherm in the region of low surface coverage. At that time also, Kiselev's attention was turning more and more towards the theoretical calculation and experimental determination of Henry's law constants for the adsorption of a wide range of molecules on graphitized carbon blacks and zeolites. And this preoccupation remained right up until the time of his death. The basis for the molecular statistical calculation of the Henry's law constant was developed first by Kiselev and Poshkus for the adsorption of hydrocarbons on the basal plane of graphite. I think the first paper in the recent series appeared in the Faraday Transactions of the Journal Chemical Society in 1976, and then more recently the approach was extended to the X and Y zeolites by Kiselev and Pham Quang Du. Part one of this series was written by Bezos, Kiselev, Lopatkin, and Pham Quang Du, and appeared in the Journal Chemical Society Faraday Transactions 2 in 1978. We see here the general molecular statistical expression for the Henry's law constant as applied to adsorption of quasi-rigid molecules. This equation is obviously written in a shorthand form, and strictly involves the multiple integration of the exponential term for all configurations of the molecule with respect to the adsorbent structure. So we have here, I've simply written, which is the convention used by some workers now, the singular integral, to represent multiple integration under these states. Obviously, the exact computational procedure and the allowable approximations must depend on the nature of the adsorption system and in particular on the complexity of the adsorbent. Not surprising, therefore, to find that the approach is more straightforward when applied to the basal plane of graphite than it is in the case with the zeolites. However, in spite of the problems encountered with the X and Y zeolites, considerable progress has been made, as we shall see, on a semi-empirical basis, as Kiselev himself has said. For a given location and orientation of the molecule, of the adsorbate molecule, the interaction energy between each atom or group of 4 centers can be represented in this way. This shows this equation gives us the usual summation with the Leonard-Jones terms, the 612 potential energy terms for the dispersion, short-range repulsion, and the polarization term, the last one, which is itself a summation term. A number of unavoidable approximations are involved in this calculation of interaction energy. For example, normally the application of the Kirkwood-Muller equation for the calculation of the dispersion constant. And in addition, there are uncertainties, of course, about the precise zeolite structure, certainly on the atomic scale, and the location of the exchangeable cations. As we see exemplified for ethane on sodium X zeolite, if we look at the left-hand curve first, we see the dashed line, which is derived from the calculated values of the Henry's law constant, and obviously the full line here is obtained by experimental measurements, which are made up of part, as you see, part calorimetric and part using the gas chromatographic technique, which I shall mention later, in the high temperature region. Now, you see that there is, in fact, a considerable difference in the location, position of those two curves. And to overcome the difficulty, the discrepancy, Kiselev introduced an empirical factor, which he called beta, for the correction of the potential energy. And this beta term is effectively a scaling factor, which in this particular case was taken, as you see, as 0.84. And by using this correction factor, this scaling factor for ethane, which was taken as a kind of standard, the other curves were now brought into quite close agreement with this same value of beta 0.84 for the series of hydrocarbons. And this is why this is referred to as the semi-empirical approach. In the case of the adsorption of noble gases by sodium X zeolite, the values of beta found to range between 0.91 and 0.94, but it was found in some exploratory work, preliminary work, that the change of the zeolite structure from sodium X to sodium Y required a change of beta to around 0.7, although it was pointed out that the accuracy of the experimental data in this case was not sufficiently high to place an exact value on that. Kiselev has drawn attention once again to the need for more precise experimental measurements on a range of carefully prepared zeolite crystals of various structures and, of course, containing different exchangeable cations. And it was his wish, certainly, that this would enable further progress to be made in this particular area. Well, now let me turn attention to another aspect of the work which I mentioned in the first place. This was the use, in the latter years, the use of the technique of gas chromatography. Kiselev and his co-workers have extensively applied gas chromatography since the mid-1970s for the determination of the Henry's law constants, as we've indicated already, and this has led them to introduce a new method for the study of the structure of adsorbate molecules and the study of the molecules in the adsorbed state, and this technique has been referred to as chromatoscopy, if that is the pronunciation, chromatoscopy. And I give here a general reference which will, I think, introduce you to the technique and the logic behind it. Essentially, this method provides a way of identifying abnormalities in the gas-solid interactions by the comparison of the corresponding experimental and calculated values of the Henry's law constant with the application of these correction terms, the beta factor. For example, just to take one particular case, it was found in the study of the adsorption of cyclopropane by sodium X zeolite that the experimental value of the Henry's law constant was considerably greater than the corrected value obtained by calculation, as calibrated against ethane. This difference was attributed to enhanced adsorbent-adsorbate interactions, which were believed to originate in the significant field gradient quadrupole contribution in this particular case. The method has been used, also extended to other systems to throw light on the structure of much more complicated adsorbate molecules, such as steroids and various alkyl aromatic hydrocarbons. And as Kiselev has pointed out again, the future application of this technique will depend, of course, on the development of other well-defined adsorbents. It's worth mentioning perhaps the recent work on the hydrogen treatment of graphitized carbon black, which certainly brings about a significant change in the chromatographic properties, but which, as far as I know, has not really been studied in any detail in a systematic manner. Finally, I should like to refer briefly to two quite different adsorbents to illustrate how gas chromatography can be used to characterize the surface properties of solids, coming to the fourth area of Kiselev's work. First example concerns a study of barium sulfate. I thought I would take this because it is so very different in character, and this work was carried out by Belyakova, who is with us at this meeting, Professor Belyakova, Kiselev, and Soloyan in 1970. These results were published in, I think, Chromatography, I believe. Two samples were studied in this work, one having a BET area of around 8 square meters per gram, and the other having an area of 2.5 square meters per gram. Plots of the low coverage heats of adsorption against the carbon number are shown here, in one case shown here, and one can see immediately that there is therefore a considerable specific contribution which comes into play in the case of the polar molecules. So we see the usual regularity of the heats of adsorption here, depending on the carbon number and the alkane molecules here, this very high degree of regularity, and then the enhanced interactions which we see in the case of the aromatic and other polar organic molecules. So there is clearly a very strong, very pronounced specific contribution which can come into play in particular cases. Now, as we see in the table here, table given in the same paper, we see the individual values listed, initial heats for benzene, and the corresponding initial heats for the normal alkane, for normal hexane, and we see comparisons with other adsorbents, the sodium xeolite, and then the hydroxylated silicas, and the graphitized carbon blacks. So all drawn up together, showing, of course, some interesting differences between them, which are due partly to differences in the dispersion interactions, which are affecting in particular the differences in that column, and to the specific interactions which will affect to some extent differences in that column, and as shown by the difference in the two corresponding values in the last column. One of the interesting things which, not, as far as I know, has not been explained about these results so far is that there is a considerable difference here, as we see, in the non-specific heats for the normal alkane. These two, for the two forms of barium sulfate, are quite different. However, the specific contributions given by the differences between the corresponding values are not widely different. This is an interesting result. The specific contribution was thought to originate mainly through the cation pi bond interaction. We've been carrying out recently some similar program of work on a series of samples of calcium carbonate, but in our case we find that the normal alkane heats are fairly constant, whilst the specific contributions vary from one sample to another, depending on the degree of exposure, we believe, of the cationic sites. So whatever is, this is work that I think is promising for the future, but whatever is the explanation, there are obviously some very significant differences here, which I think one could explore further. My second example concerns the characterization of the molecular sieve silicalite 1, which has the ZSM5 type of structure, but supposedly without the aluminium content. Here we have, as you see, replotted the results obtained or presented in a very recent paper by Kiselev and his co-workers. The work here, Kiselev, Lopatkin, and Scholger, published in 1984. And we find that there are, in fact, some interesting differences here. The calculated values taken from the original paper follow quite closely the experimental values as reported by the Russian workers, but our own results fall short of these. And in some of, there is a slight but quite significant difference here. On the other hand, both of these curves, of course, show a considerable enhancement in adsorption energy over the baseline, which is obtained for macroporous silica gel, where there is virtually no enhancement coming about through the effect of the micropore filling. In our experience, silicalite is extremely difficult to reproduce exactly, And we are now looking for the maximum enhancement for this type of pore structure. This we believe to be very important, useful technique to explore these differences and perhaps to show the uniformity of the pore structure in this particular molecular sieve zeolite, where the pores have a diameter of around 6 angstroms. We find, just one further point perhaps worth just mentioning briefly, that you see here a point that we've reported for normal pentane, which in fact at this temperature is quite close to the value given in the original paper, strangely enough. Isopentane is not able to penetrate, or is only able to penetrate into the pore structure to a limited extent, gives a pronounced tailing effect in the chromatographic experiment, and therefore one cannot interpret the results in this manner. Well, I hope that in the course of my talk this morning that I've been able to convey the impression, at least of the remarkable scale and indeed influence of Kiselev's work. I have here tried to summarize, I'm sure in an inadequate way, really. It's impossible to do justice to all the contributions that he has made over the period of his life's work of 50-odd years. But I've tried here to summarize what I feel to be at least the main areas of the contributions, the progress that he and his co-workers have made under those particular headings. I think that it's fair to say that generally speaking, Kiselev was not a pioneer in the sense of originating the particular experimental or theoretical technique which he employed, but what he did do so remarkably successfully, in my view, was in fact to apply such a wide range of different experimental and theoretical techniques, and to do so in such a comprehensive and thorough, painstaking manner, and to do so, as I said in my abstract to this talk, apparently with a grand design in mind. So you can see almost from the very beginning, when he made such an enormous impact on us, when he presented 3 papers at the Congress in 1957, and many other contributions during the course of the discussion, one could almost begin to see then the shape of his life's work, the way in which the whole subject was going to develop. In my view, I hope that you'll forgive me for these flights of fancy, but in my view, his achievements had the grandeur and even the lyrical quality of a symphony by Mahler, or the magnificence of one of our English cathedrals, say Salisbury, with its soaring spire, which Kiselev admired so much. He was not always fortunate in his choice of materials, as we've seen, but he overcame the difficulties that he had with inadequate materials, I think, remarkably successfully. But he was extremely fortunate in having such a loyal and talented group of co-workers. I've put together here just a few of their names. This is not comprehensive by any means. These are a few of the names of workers who have been with him, who worked with him over a period of many years. Some of them, in fact, going right back to the 1950s, and some I met also for the first time in 1965. And it is, I think, to the credit of Kiselev and to all those co-workers that their work has been so highly successful. I'm sure that many of them will continue to follow his teaching and example and go on hoping for the best in our joint search for the best of all possible surface chemical worlds. Just finally, on a somewhat sad note, I did find in my collection this picture, which shows, it's not very clear, but it shows Kiselev and the late Geoffrey Parfitt walking together on a beach in North Wales at the time of a UChem meeting which we ran on the surface, on chemistry of interfaces, the first UChem meeting on this subject in 1968. Thank you very much. Possible.